right, so let's go ahead and start filling in for organic notes. Organic chemistry is the study of carbon compounds. Carbon compounds. It's got to have carbon in it to be considered organic. In organic compounds, carbon atoms are found bonded to other carbons and others near carbon. So going to see lots of nonmetals. It's going to be a lot of carbon and hydrogen, oxygen, carbon, hydrogen, oxygen, nitrogen. So occasionally some sulfurs and phosphorus you might find in there. Okay, and other halogens like chlorine, fluorine, bromine, stuff like that. Most importantly, the carbon atoms also bond to other carbons and can form chains from like 2 all the way up to 2,000 atoms in length. So last year when you studied biology, you studied a lot of these organic compounds like nucleic acids, the DNA, the proteins made of amino acids, the carbohydrates made of the monosaccharides, the disaccharides, those things. And then the lipids, they had the glycerol and the fatty acid chains. These are all organic compounds. They're natural ones. They all have lots of hydrogen and carbon in them. But carbon is the main aspect to identify it as being organic. So, carbon has 4 valence electrons. Those 4 valence electrons, that's why carbon does 4 covalent bonds. The 4 covalent bonds allows it to do branch chains, ring structures. So you can see carbons doing single bonds. It could be all single bonds like so, and bond to another carbon. You could have carbons that have double bonds. Okay, so they still can form the chain because then they'll bond to 2 other things like so with a double bond. They can also do triple bonds, right, and bond to 1 other thing. But they're always going to have 4 bonds around them. And usually the bonds attach to like hydrogens on the outside. Okay? But that's how they have the ability to form these long chains. They're always going to have 4 bonds around them. This is, 1, 2, 3, 4. 4 bonds around each carbon. And that's why we get so many possibilities when we're talking about organic compounds and carbon being the central main piece of it. All right, so your turn. Based on this definition, go ahead and circle which ones that you think are organic. Take a moment to do that. Okay, so how about this first one? What do you think? Is this one got some carbon and hydrogens in this ring? That one's definitely organic. How about ammonia, NH3 in the middle there? No carbon in it at all, so that one is not organic. How about the Na plus Cl minus? No, what type of compound is that? That's an ionic compound. An ionic compound is always going to have a metal, non-metal, so you're not going to see any like carbon chains in that. How about this one down in the lower left corner here? Yes, definitely, and over to the right there. Yes, this one right here is called propane. The one that we just circled, this 3 carbon one, this one. This is propane. Anybody know of propane and where you use it? It is a gas, and it's mainly used in barbecue grills, yes. This one over here is also organic. This one's called ethanoic acid or acetic acid, but it's vinegar, basically. The stuff we clean with, the stuff we put on our salad dressing, that would be vinegar over here to the right. All right, so the simplest organic compounds which contain the elements carbon and hydrogen, we call them hydrocarbons. And the simplest one is methane, CH4 here. And if you remember, what was the shape of methane? What shape did it form with methane? 4 things attached, no lone pairs. 4 things attached, no lone pairs. Tetrahedral, very good. Remember the ball and stick model? You have 1 on each side, it flips and so forth. Methane is the main component of natural gas which comes out of our outlets in the classroom and we use for the flame test lab and things like that. And it's what normally comes out of most people's stoves and some people's heating systems in their houses they use methane, they use natural gas there, okay? Now let's talk about alkanes, alkenes, and alkynes. So an alkane is a saturated hydrocarbon that has only single bonds. This is the part where you note the difference, single bonds. Now, this is a drawing. I'm going to show you what it looks like from its Lewis dot structure. For the alkane here, this is ethane. Ethane basically is two tetrahedrals put together, and there's all single bonds. All the hydrogens are single bonded, the carbons are single bonded, has the maximum number of hydrogens it can possibly have. An alkene, though, an alkene is considered unsaturated, and this is why, because it contains one or more double bonds. So this is where you need to highlight the double bond, double covalent bond. Now, if I draw the Lewis dot structure of this one, it would look, I'm going to draw it up here, it would look more like this. You have a double bond in between them, and as you can see, by creating that double bond, we have 2 less hydrogens than we did when we had the alkane. On the alkane, we had 6 hydrogens around it. This one only has 4. So it doesn't have the maximum number of hydrogens that it could possibly have. So we call this one unsaturated. Has a double bond, you can recognize it as being unsaturated. The last one of these is called the alkynes. And probably could have guessed it, but the alkynes have a triple bond, at least one of them in there. This one's gonna have triple bonds, okay? And it's also unsaturated because it doesn't have the maximum number of hydrogens possible. If we draw a Lewis dot structure for this one, it looks like this. Okay, it's a nice linear shape, but there's only 2 hydrogens on the alkyne there. That's called ethyne. We have ethane, ethene, and ethyne. The ending of the name just changes. But we only have 2 hydrogens there, not 6. The maximum you could have is 6. We only have 2, so that's definitely unsaturated. Take a moment to make sure you draw either the ball and stick model or the Lewis dot structure, so you can remember that the alkanes are going to have all single bonds. The alkenes are going to have at least 1 double. And the alkynes are going to have at least 1 triple bond. So let's continue on. Saturated versus unsaturated. Organic compounds can be saturated or unsaturated. A carbon chain is saturated when it only contains single bonds between the carbon atoms. Each carbon is bonded to its maximum number of hydrogens, and that's why we say it's saturated with hydrogen. Carbon chain is unsaturated when it contains at least 1 double bond or triple bond between the carbons. So an alkene or an alkyne fits the description as being unsaturated. An alkane, only single bonds, is going to fit the description of being saturated. Now, I'm sure you've heard of saturation in terms of they say on commercials and things about saturated fats or unsaturated fats and which are the good ones to eat and which ones are the bad ones to eat. And you'll notice there, like, the saturated stuff is the stuff that's in, like, animal fat. It's solid at room temperature. It's not easily broken down by the body, and that's why it can, like, cause hardening of the arteries, the atherosclerosis, or can clog arteries and cause heart attack or strokes and things like that. The unsaturated fats, are really good for you. They're the ones that have double and triple bonds in them. I'm sure you've heard of, like, omega fatty acids or omega oils. Those ones have double bonds in their chains, omega-3s, omega-6s, omega-9s. They have double bonds in their chains. They're the stuff that's in, like, fish oil, canola oil, olive oil. Those are the ones that are liquids at room temperature. Those are more easily broken down by the body and therefore would be considered good fats. Okay? Here on the unsaturated carbon chains are more reactive. those double, triple bonds are more easily broken than the single bonds of the saturated ones. So breaking those molecules down, the alkenes and alkynes are much easier than breaking down the alkanes. So looking at our chart here, solid at room temperature, bad fat. So the butter, cream, fatty meat, steak and stuff that has the little marble in it that you see, these ones are the ones that are, you can have some, you just don't want to overdo it because then that's where you run into some of these health issues. Liquid at room temperature, good fat, olive oils, canola oils, the fish oils, all the, you know, anything that's liquid at room temperature that's an oil is usually pretty much in the unsaturated fat category. Okay? Functional groups. Let's talk functional groups. There are 3 functional groups and then the benzene ring that you have to know. So if you're looking up here, how do I know what a functional group is? It's going to be on the end of the carbon chain. So that's what this R is telling me right here. This means this is a carbon chain. So I have like an OH attached to C's, like so. It's on a carbon chain. So this R value is like it's attached to C with, I don't know, however many long you can put on there. Doesn't necessarily have to be 2, it could be 3, it could be 4, it could be 10, it could be 100. Just to, you know, if you have an OH on the end though, that makes it an alcohol. This is called a hydroxyl group, the OH on the end. And basically, it just adds that extra added thing to it that makes it an alcohol. Now the 1 carbon, and you noticed this in the IMF lab, I'm sure. This is the OLs. We changed the ending so it's not methane anymore. It now becomes methanol. And if we had the 2 carbons, it would be ethanol. Okay, you just change the ending to OL to put it in the alcohol group. That means it has the OH on the end. The next one is going to be the carboxylic acid, also known as an organic acid. Its group is a C that's double bonded to an O and then an OH. So you need to see all 4 of those hooked together like so. So this part, that is going to make it a carboxylic acid. We changed the ending of the name to oic acid, so it's not ethane anymore, it becomes ethanoic acid. And you're going to see COOH attached to the end of the molecule at the end of the chain, and that will put it in the carboxylic acid grouping. The last functional group on here that we want to look at is the amine group. You'll see an NH2 on the end, or an NH. Somewhere you'll see N with H's on it. That's going to put it in the amine group. Now, if you remember from last year in proteins, and why do they call them amino acids? Well, because the amino acids have amine groups all over them. And they form those hydrogen bonds in between DNA, and they also form hydrogen bonds to fold the proteins. So amino acids all have amine groups on them. And I'd like to name this one because this one only has 1 carbon. And then the amine group, we would call it methylamine because there's 1 carbon group off of it. If it had 2 carbons off the chain, we'd call it ethylamine. 3 carbons, it would be propylamine, and so forth. Now the benzene ring down here at the bottom, this one has 3 double bonds in it. 3 double bonds in it. And it's a ring and it has hydrogens all around. This one's non-polar because it's a hydrocarbon. So it's only going to have London dispersion forces. Whereas, say, you know, this guy, NH2 groups, N bonded to H's means it falls under hydrogen bonding. This one has an OH, that one's also hydrogen bonding, and this one also, we know, would fall under the intermolecular force of hydrogen bonding. But you can, the double bonds can equally spread across, so that's why you can draw it with the circle. But benzene, C6H6 is a nonpolar solvent used in lots of manufacturing, but it's very toxic. So you have to be, well equipped with all the safety gear because you wouldn't want to breathe it in, cancer-causing stuff. But used a lot in industry to make other compounds. So now what I want you to do is circle the functional group and label like what functional group it is. Like for instance on this one, what's the functional group? The NH2 is the functional group, right? And which category does that fall under? That would be an amine. So that's what I want you to do, is circle them and write down what type of functional group it is. All right, so let's look at this next example, this one in the middle here. Where's the functional group for that one? The OH, very good. The OH is the functional group. And if it hasn't just an OH, it's going to be a what? An alcohol. Very good. That one's an alcohol. This one over to the right, let's take a look at it. This one. What does it have on it? NH2. So that NH2 is going to be an amine. Very good. Now let's look at this one in the middle right here, this guy right here. What do we see there? We see an OH, but what also do we see? We see the other oxygen double bonded to the carbon. In that case, what do we have? Carboxylic acid. Very good. Carboxylic acid. So that one, you would circle the COOH. So the C double bonded to the O with the OH, and that would be your carboxylic acid. Over to the right here, this one. What's this one going to be? What do we see on the end? NH2. So that's also a amine. That's an amine. How about down here in the lower left? That is also a C double bonded to an O with an OH. Very good, right there. That is a carboxylic acid. The last one, the bottom right there, has actually two things in it we should identify. We see benzene, good. What else do we see? An alcohol, very good. So the OH is the alcohol. But we also see the ring, which is a benzene. So we see both of them in there, and we would want to identify them both. Okay? You can have more than one functional group. True. Yes, you can. All right, so now what I would like you to do is I'd like you to take a moment and draw the Lewis dot structures for this one, CH3OH and C2O there. Go ahead and take a moment to draw those. What do we do first when we're drawing Lewis dot structures? Count the valence electrons. First count your valence electrons. Then you need to identify central atoms and start arranging your ligands around the central atoms. Remember, hydrogen can never go in the center. Okay? Hydrogen's never going to go in the center. So go ahead and take a moment to draw those. Okay, so here, carbon has 4 valence electrons. Each hydrogen is 1. So 1 times 3 gives me 3. The oxygen brings in 6. This hydrogen has 1. So that totals up to 14 valence electrons. Now I know hydrogen cannot go in the center, so I'm going to put carbon and oxygen in the center. Hydrogen can't go in the center. And this 3 here tells me that there's going to be 3 hydrogens off of the carbon, like so. Then this H is next to the O, so I'm going to put it off of the O, like so. 2, 4, 6, 8, 10. Okay, 10. So now I have 4 electrons left. Which element still needs electrons in order to be stable? The oxygen, right? It's only got 2 bonds. This one right here and this one right here. So it still needs 4 dots, like so. Now, the thing is, we want to determine the shape around the carbon. We need to determine the shape around the carbon. So here, if we're looking at this carbon, it has 4 atoms attached to it, right? 4 atoms, but no lone pairs. So what would be the shape around that carbon? What shape is it where you have 4 things attached and then you have no lone pairs on the central atom? So this one would be a tetrahedral, yes. This one, tetrahedral. Good. So this carbon has a tetrahedral. How about that oxygen? Around the oxygen, what shape would that be?
Bent.
This would be bent. If you look, you have the 1 and the 2 atoms, and then you have 2 lone pairs. So yes, the oxygen actually is a bent shape around it. Now let's look at the middle one here. This is formaldehyde. Once again, we have 4 electrons for carbon, 2 times 1 for the hydrogens. Hydrogen has 1 valence electron each, and then 6 for that. So this adds up to being 12 total. We have 12 total to work with, right? We put the carbon in the middle, we attach the ligands, the hydrogens, and then the oxygen. So that's 2, 4, 6. Now I have 6 electrons left. Where do I put them first? I put them around the oxygen. Okay, so I used all of my 6, but what happened? I ran out. Yes, and carbon is not going to be satisfied with only 6 electrons. So we need to take off a pair, and create a double bond here. Now, this means there's 3 atoms attached and then no lone pairs on the central atom. What shape is that one going to be for our carbon? This is going to be trigonal planar, yes. The flat triangle. So that one's a T-planar for the central atom there. If you look over here at the benzene, you don't have to draw it, but let's look at the carbon. Let's take a look. If we're looking at any of the carbons, they all have 1, 2, 3 things attached and no lone pairs. So what's the shape around every single carbon? 3 things attached, no lone pairs. This one's also T-planar, right? Every single carbon in the ring has 3 things attached with no lone pair, so it's going to be a trigonal planar shape. We need to be able to identify the shapes of the carbon atoms. We're almost done, so let's keep going here. So the trigonal planar, yes. Polymers, let's talk polymers. Polymers under certain conditions, an alkene. Alkenes, things with double bonds, undergo addition reactions with themselves to form long chains. So this double bond here is going to break, and then it adds on another one to it, and it keeps adding, and then it forms this very, very long chain. So PVC, ever heard of PVC?
Yeah.
What is
No.
made out of PVC? Well, PVC is a type of plastic, but does anybody know what we typically use PVC? It's pipes. Pipes are made out of PVC. Very good. This one down here is showing you they have fluorines as their monomer with the double bond. That polytetrafluoroethene, Teflon, non-stick on the pans. That is also a polymer, okay? But the monomer is going to be the alkene that has a double bond. You break that and add it to the chain, and then you get your polymer. So let's take a look at one of these. Extremely long molecules consisting groups of atoms that repeat in a regular pattern. The monomer is the small, simple organic molecule from which it's made, and the alkenes are the ones that make the plastics that we're going to be looking at here. The synthetic, these ones are man-made, not natural, not made by the natural world. So here's an example of polyethylene, which is plastic, where you have the alkene with the double bond here. Here's the alkene with the double bond, the monomer. That breaks the bond, and then it adds on more units, forming this big, huge, long repeating chain, as you see over here. And these dashes are just over here, like, because you could just keep adding more to it. You would just keep getting bigger and longer. And that's polymer. They're saturated, as you can see here. Hydrocarbons, not easily broken down. That's why a lot of these plastics and things that are polymers, that are synthetic, are not biodegradable. Bad for the environment, right? So let's look again here. Polymers can be natural or synthetic. So some natural ones are going to be like DNA, proteins, carbohydrates, starch, wool, silk, any of those that are made from natural means. Silk is made by a worm, wool is made by the sheep, So lots of these ones would be biological in nature, come from the natural world. Fatty acids, lipids, candle wax, stuff like that, that would be made by beeswax. Okay. Examples of synthetic: nylon, polyethylene, polyester, Teflon. You'll see some other ones, maybe like Kevlar, which is found in like soldiers' vests and things as armor. But they sound synthetic. PVC, polyethylene, polyester, nylon, Teflon. These ones do sound like they are in that class of category. Okay. So examples, a lot of nylon and polyester and other things are in clothes. Okay, so practice, determine the monomer and draw the structure of the monomer for each of the following polymers. So we need to construct an alkene that has a double bond here. First, figure out the subunit. Then all you would have to do is do what to that? Take it out and create a double bond between the carbons. Okay, you try the next one to create the monomer real quick. Okay, so make my H a little bit better down here. CH3. Over here, all we have to do is figure out a unit, and they're pretty much the same repeating one, and then change it to find the monomer, create a double bond between the carbons, and that would be the repeating unit, the monomer, for that particular polymer. Any questions on that? Pretty easy stuff.